Good morning, everyone. I'm Jordan Keller.
I'm Ngozi Lawanson.
And I'm Mary Ryan Gilmore.
And we are all engineering students at the University of Texas. So, we're going to be talking about something super exciting, the Olympics. So, how many of y'all watch the Olympics? Yeah, pretty fun. Have any of y'all ever thought about being in the Olympics? Maybe? Okay, so what events would y'all want to be in? Gymnastics?
Curling.
None of y'all mentioned engineering. Have you thought about being an engineer for the Olympics? Probably not. Well, today we're going to introduce you to some really cool things that engineers are doing for the Olympics.
Okay, so when someone talks to me about being an engineer at the Olympics, I'm thinking, am I going to build the stage? What could I do? And I don't know about you, but something that I've never thought about is the contribution that engineers make to sports, to the athletes that compete in the Olympics. And so today we kind of wanted to show you your path to the goals as an engineer, and some of the things that engineers are doing to help these athletes go faster and stronger than we ever thought possible. So we wanted to talk to you about the technology that swimmers are using through the swimsuits and the swim caps and goggles, and then perhaps the coolest new Olympian in the Olympics this year, Oscar Pistorius, who was a double amputee who ran with able-bodied runners, and show you how engineers really made his dream come true.
All right, do we have any Michael Phelps fans in the room? Anyone? All right, well, we're about to relive one of his typical yell-at-your-TV moments at the 2008 Beijing Olympics. All right.
Oh, yeah.
Oh well. I wonder what else will come up.
Cabin's still leading for Serbia. Is it going to be the seventh hurdle that he's going to fall at? He's coming back. He's coming back very strongly, Michael Phelps. Surely he can't do this from this pace. Michael Phelps is coming back at 5. Is he going to get the touch? No, he's not. Oh, no! He's got it! Oh, he's got it! Oh, Michael Phelps! Oh, he's tired. Oh, my word! No, he's got it. He's got the gold. 50.58. Michael Phelps, 1/100th of a second. I cannot believe he's just done that.
One of my favorite parts of the Olympics is watching swimming. It's definitely, I think, funner to watch when it's super close. If we go ahead and look at the next slide, if we actually look at the times over here, we have 50.58 and 50.59. That is 1/100th of a second. And honestly, that's really what it's coming down to in the sport. I mean, you don't win a swimming competition by a matter of a couple seconds, like 5 seconds, Typically, you win it by a very small margin, even a fraction of a second like that. And this is where engineering comes into play, because the technology that's being built and innovated right now has the power to push someone 1/100th of a second ahead of their partner. So that's what we're going to look into today. One example of that is Vito's fast swim line. And now if we think for a second, like an engineer, what should we model a swimsuit after to make it as fast as possible? Okay, so if we think rationally for a second, and a genie comes up to me and says, Mary Ryan, I will turn Michael Phelps into whatever ocean fish that you want to when he gets in the water. And after my initial excitement that, my genie finally came in my time of need, it's about time. Of course, I don't know about y'all, but I would choose the fastest one. Doesn't that make sense? That's common sense. And that happens to be the shark. And a couple of features that make the shark a little bit different than your average fish is the scales. And these are called denticles. Now, you notice something about these scales, okay? They're rigid. They kind of wave back and forth. Now, let's look at what water does on a smoother surface. As you can see, the speed of the water on a smoother surface is smaller lower than the water flow farther away from the surface. And what these ventricles do is they kind of correct that change in speed. Because if you look down here, there's a significant difference between this wave and this one. It's going to create a circular motion. You understand? These are called eddies. So what you want to do is minimize the eddies, because the eddies are slowing you down. So as the water passes through these grooves, it's like passing through a Starbucks straw, one of those really little coffee straws. And you know, if you take a straw with a really big radius and one of those small radius straws, and you pass water through it at the same amount of water at the same rate, it's going to go faster, slower, faster. Okay, so that's what it's doing. It moves this water closer to the surface a little bit faster than it would on a smooth surface.
Okay, so do any of y'all have any friends that are swimmers, or are any of y'all swimmers yourselves? Yeah? Okay. So what's one trick that y'all do before a race to get ready? Shave, right? So aside from wanting smooth legs because that feels nice, why would you shave? Anyone know, like scientifically maybe? Right, you want less friction. So do y'all understand what friction means? No? Okay, good. So, okay, think back to when you were a little kid and you would run around the floor in your socks. What was more fun to slide on? The hardwood floor or the carpet? Hardwood floor. So why was that more fun?
Faster.
You go faster, right? Yeah. So why do you think the hardwood floor was faster than the carpet? Less friction. Good job. Yeah, so when you go on the carpet, right, there's a lot of friction, and that resists your flow. So you're going to kind of stop and fall over and maybe get a carpet burn, right? Ouch, don't want that. So, in the same sense, swimmers don't want to be experiencing a lot of friction while they're swimming, because that's going to slow them down, and they want to go fast. So, the engineers at Speedo developed this really cool computer modeling system that models swimmers in the water and determines the areas on their bodies that are subject to the most friction. So if you look at this swimmer, see all these blue and green regions? That means a lot of friction. That's bad. That's going to slow them down. And so the engineers have this really cool idea to put in these areas this low friction fabric to reduce the friction on the swimmer. So what does that look like engineering-wise? If you look at this, these blue lines show how water is flowing over this little gray thing's a swimmer, okay? Over the swimmer in the water. And we want these smooth lines. These little squigglies are like the eddies, they're turbulent motion. It's not going very fast. We don't want the squigglies. And so on a really rigid surface, that's going to slow them down. That's like when you have hairs. We don't want that. And so that's why these swimsuits are really sleek and smooth and allow the swimmer to go faster. Another thing we're going to look at is the shape of them. And so in this picture we have like, a rectangle that has corners and edges. This isn't going to go so fast through the water, right? It's a weird shape, slowing you down. We want a more sleek shape. And so the engineers had to think about this when they were designing the goggles. So if you think about it, when you jump in the pool and you're wearing goggles, what's your first reaction? Oh no, where's my goggles? Did they fall off, right? So the engineers had to think about all these forces acting on the goggles when you jump in the pool and when you are swimming. And then they also had to think of the design that was going to have the least amount of drag or friction. And so they developed these goggles as well as the swim caps, because if we remember right, the head on that picture was really blue, right? We don't want the blue. And so these goggles and swim caps not only reduce friction, but they also reduce drag because of their sleek shape, and they also don't have a lot of bumps and points. So this would be what the swimmer would look like in the water, and all these lines are really smooth.
All right. Now, talking about how engineers make the impossible possible. Did anybody see Oscar Pistorius run in the Olympics? It was super cool, right? So he has these amazing legs that are called cheetah legs because they kind of look like the hind leg on a cheetah. to sort of mimic the energy inputs and outputs that we as runners have whenever we go. And so Usain Bolt is super fast, of course, fastest man in the world, and he has a little bit of an advantage over Oscar Pistorius because he has these huge calf muscles and these really long feet that allow him to do a lot of work and put a lot of mechanical work in to get him to the finish line super fast. And so Oscar Pistorius has to do, some different things in order to put out the same amount of work. And so we want to see how these two legs work so that we can see how he does that. So has anyone taken physics and know about energy conservation? Does anyone know what that is? Care to explain? You? Oh, no, sorry. It's okay. It's really simple concept. So when you have a system, basically the amount of energy that's in it, no matter what kind of energy it is always the same. So there's a thing called potential energy, which is the energy you have when you're stopped, when you're not moving, and kinetic energy, which is the energy you have when you're in motion. So if you think about a spring, when you compress the spring all the way down, it has all of this energy pent up in it, and that's potential energy, so that when you let it go, it springs up really fast, right? And that's the potential energy being converted into kinetic energy. And so Oscar Pistorius' legs work the same way. So when he touches the ground, this little bottom part right here stores all of that energy of his weight hitting the ground. And then when he jumps off, all that potential energy is converted into kinetic energy, which is really what's propelling him towards the finish line. And so our feet kind of work the same way. When we jump down, our ankles store all that energy. We shift to our toes to jump back up again. And so it's kind of working the same way, but there are still some things that he might be missing. Can anyone think of something that, even with this, Oscar Pistorius might be missing that would be a problem in a race?
Balance.
Balance, right? And so, actually, a fun fact, Oscar Pistorius cannot stop moving when he has these legs on, because if he did, he'd fall over. And a reason why that is because he doesn't have ankles. So, this comes into a problem at the turn. So, in our ankles, they're called a hinge joint. And so this allows us to kind of lean over, when we turn, we can walk like this. But Oscar Pistorius doesn't have that advantage. So he has to really swing his arms around. If you've ever seen him run, you might notice he uses his arms a lot more and uses core muscles in order to make those turns that other runners can make. Another problem he has is really at the start of the race. So let's look at Usain Bolt. He has this really cool starting position. He has his legs all stretched out. And the reason that he does that is because we have a muscle in the back of our calf, and it's called the Achilles tendon. And so if he puts his leg back, he can stretch that Achilles tendon as far as it can go. If you think about a rubber band, the further you stretch it, the more it snaps, right? And the more power you get when that rubber band snaps closed. So the more that he stretches out his Achilles tendon, the more force he has when he gets off that starting block. So Oscar Pistorius, of course, he doesn't have an Achilles tendon, he doesn't have calf muscles, so he doesn't have that advantage. So the result is a slower start. And what's really amazing is that there have been so many things done by engineers for Oscar Pistorius to be able to run against able-bodied runners. But what's even cooler is that there's still so much that has to be done in order for him to run faster than, say, Usain Bolt. And that's where you come in. As, future engineers or future whatever you want to be, there's so much creativity in this group. And, maybe you don't even know how much that you possibly can do. And with the right sort of training in math and science, you could be the next person that makes Oscar Pistorius able to run against Usain Bolt, possibly.
So with all of that, I hope you all realize how cool engineers are and that engineering is awesome. So we just want to say thank y'all for your time and hook 'em horns.